Welcome back, Math Warriors. Today we're diving into Chapter 3 of our pre-algebra series, Factors, Multiples, and Rational Numbers. Now, I know that title sounds like a lot of math jargon thrown into a blender, but honestly, this unit is just about understanding the DNA of numbers, what they are made of, and how they fit together. By the end of this video, you'll know how to find the building blocks of numbers, how to tame giant monster fractions, and you'll finally understand what a rational number actually is. Let's get started. Before we hit the main topics, we have to stop mixing up two crucial words: factors and multiples. Think of factors as the ingredients. They break numbers down. Factors are the smaller whole numbers that multiply together to make a bigger number. For example, the factors of 12 are 1, 2, 3, 4, 6, and 12. On the other hand, think of multiples as the giant products. They build numbers up. It's what you get when you skip count. Multiples are bigger than the starting number. For example, the multiples of 12 are 12, 24, 36, 48, 60, and so on. Just remember, factors break it down, multiples build it up. Let's talk about the GCF, or greatest common factor. This is crucial for simplifying fractions later. Imagine you have two numbers, 12 and 18. The GCF is simply the biggest ingredient they both share. First, list the factors. For 12, 1, 2, 3, 4, 6, 12. For 18, 1, 2, 3, 6, 9, 18. Next, look for the matching numbers. They both have 1, 2, 3, and 6. Finally, pick the greatest one. It's 6. So the GCF is 6. But what if the numbers are huge? If I asked you to find the GCF of 120 and 180, you definitely wouldn't want to sit there listing factors one by one. You'd be there all day. For big numbers, we use a tool called prime factorization, or factor trees. We're going to break these numbers down until we hit their atomic level, the prime numbers. Let's break down 120 first. What two numbers multiply to make 120? Let's go with 12 and 10. Are those prime? No, so we keep going. 12 breaks into 3 and 4. 10 breaks into 2 and 5. The numbers 3, 2, and 5 are prime, so we stop there. But 4 is not. 4 breaks down into 2 times 2. Now, look at the bottom of the tree, the leaves. We have 2, 2, 2, 3, and 5. Now let's do 180 quickly. 180 is 18 times 10. 10 becomes 2 and 5. 18 becomes 2 and 9. And 9 becomes 3 and 3. The final leaves are 2, 2, 3, 3, and 5. Now for the magic. To find the greatest common factor, we play a game of Go Fish. We look for pairs that exist in both trees. Both lists have a 2. That's one match. They both have another 2. That's a second match. Does 120 have a third 2? Yes. Does 180? No. So that extra 2 is out. How about threes? Yes, they both have a 3. Does 180 have a second 3? Yes. Does 120? No. So that extra 3 is out. And finally, they both have a 5. The greatest common factor is simply the product of these matches. 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 60. So the GCF of 120 and 180 is 60. It works every time, no matter how big the numbers get. Next up is the LCM, or least common multiple. This is the key to adding and subtracting fractions with different denominators. Think of this like two different bus schedules. Imagine bus A stops every 4 minutes and bus B stops every 6 minutes. When is the first time they will both be at a stop at the exact same time? Let's list the multiples. Bus A stops at 4, 8, 12, 16. Bus B stops at 6, 12, 18. The first number they match on is 12. That is the least, or smallest, common, shared, multiple. So the LCM of 4 and 6 is 12. But wait, what if we go back to those massive numbers 120 and 180? Listing multiples for those until they match would take forever. Instead, we can use the prime factor trees we already made. Let's look at those lists of ingredients again. To find the least common multiple, we need to build a mega number that is big enough to contain both 120 and 180. We do this by holding a competition for each prime number. First, let's look at the 2's. 120 has 3 2's. 180 has only 2 2's. Who has the most? 120 does. So the winner is the group of 3 2's. Next, look at the 3's. 120 has 1 3. 180 has 2 3's. Who has the most? 180 does. So we take the pair of 3's. Finally, the 5's. They both have exactly 1 5. It's a tie. So we just need 1 5. Now we just multiply the winners together. 2 times 2 times 2 equals 8. 3 times 3 equals 9, and the 5. 8 times 9 is 72, and 72 times 5 is 360. So the LCM of 120 and 180 is 360. It's the smallest number that both 120 and 180 can divide into perfectly. Now, you might be asking, what if a number is in one tree but completely missing from the other? That's a great question. Remember, the rule is winner takes all. We are looking for who has the most. If one number has a factor and the other has 0, the one with the factor wins by default. Let's look at 12 and 14. 12 is made of 2, 2, and 3. 14 is made of 2 and 7. First, the 2's. 12 has 2 2's. 14 has 1 2. Who has the most? 12 does. So we take the pair of 2's. Next, the 3's. 12 has 1 3. 14 has 0 3's. Who has the most? 12 does. So the 3 goes in the box. Finally, the 7's. 12 has 0 7's. 14 has 1 7. Who has the most? 14 does. So the 7 goes in. Now we multiply. 2 times 2 equals 4. 4 times 3 equals 12. And 12 times 7 is 84. So the LCM of 12 and 14 is 84. Just remember, when building the LCM, you need the biggest version of every single ingredient that appears on the screen. All right, next up, we're going to tackle the trickiest part of this chapter. This isn't just a complex fraction, it's a monster. Look at that. We have addition, subtraction, multiplication, and a giant division bar in the middle. It looks terrifying. But I have a secret for you. We don't solve this all at once. We treat it like two tiny separate problems. We solve the attic, the top, and then we solve the basement, the bottom. Step 1, the attic. 1/2 plus 1/3. We need a common denominator, which is 6. That gives us 3/6 plus 2/6, which becomes 5/6. The top is just 5/6. Now let's go to the basement. Step 2, the basement. we have subtraction and multiplication. Order of operations tells us we multiply first. 1/2 times 1/3 is 1/6. So now we have 5/6 minus 1/6. That gives us 4/6. So let's look at the whole picture again. The monster is gone. Now we just have 5/6 divided by 4/6. Now we covered dividing fractions in detail back in Chapter 2 of this pre-algebra series. But for a quick refresher, remember the golden rule. Keep, change, flip. Keep the top, which is 5/6, change division to multiplication, flip the bottom to 6/4. Look, we have a 6 on the bottom and a 6 on the top. They cancel each other out perfectly. What's left is just a 5 on top and a 4 on the bottom. The final answer is 5/4. We took that giant, scary mess, used all 4 math operations, and turned it into a simple answer. Okay, time for the star of the show. What on earth is a rational number? Look at the first 5 letters of the word. R-A-T-I-O. Ratio. A rational number is just any number that can be written as a ratio or a fraction of 2 integers. But to really understand this, we need to look at the family tree of numbers. Think of numbers like a set of nesting boxes or Russian nesting dolls. At the very center, we have the natural numbers. These are your counting numbers, 1, 2, 3, and so on. If we take the natural numbers and just add the number 0, we get the whole numbers. Notice how the natural numbers are inside the whole numbers? Every natural number is also a whole number. Now let's wrap a bigger box around that. If we add negative numbers, we get the integers. So, -5, -1, -10, and so on are integers. Finally, the biggest box of them all is the rational numbers. This includes all the fractions and decimals between the integers. Here is the cool part. Because the boxes are inside each other, a number can be more than one thing. Take the number 5. Is it natural? Yes. Is it whole? Yes. Is it an integer? Yes. Is it rational? Yes, because we can write it as 5/1. How about -2? It's not natural or whole, but it is an integer and it is rational. Basically, if you can write it as a clean fraction, it lives in the rational neighborhood. If it's a messy, non-repeating decimal that goes on forever, like pi, it lives totally outside these boxes. Now that we know what they are, how do we know which ones are bigger? When in doubt, sketch a number line. The number further to the right is always bigger. But this gets tricky when we deal with negatives. Let's try a hard one. -2/3 versus -3/5. Your brain might want to say 3/5 is bigger because 3 and 5 are bigger numbers, but with negatives, everything is backwards. Step 1 is to ignore the negative signs for a moment and get a common denominator. The LCM of 3 and 5 is 15. That turns -2/3 into -10/15 and -3/5 into -9/15. Now we have -10/15 and -9/15. Because the denominators are the same, we can ignore them and just compare the numerators. Look at the top, -10 versus -9. -9 is closer to 0 and sits further to the right, so it is the bigger number. That means -10/15 is less than -9/15. Let's translate that back. -10/15 is just our original -2/3, and -9/15 is -3/5. So the final answer is -2/3 is less than -3/5. Now let's try a mixed battle, a negative fraction versus a negative decimal. Compare -4/5 and -0.9. You can't compare apples and oranges, so convert the fraction to a decimal. 4 divided by 5 is 0.8, so the fraction becomes -0.8. Now compare -0.8 and -0.9. Which one is closer to 0? -0.9 is deeper in debt, and -0.8 is closer to being positive. Since -0.8 is on the right, it wins. So we know that -0.8 is greater than -0.9. Switching it back, -0.8 is just our original fraction, -4/5. So the final answer is -4/5 is greater than -0.9. Always check the number line. And that is a wrap on Pre-Algebra Chapter 3. The best way to lock this in is to practice. Try a few problems from your textbook right now while it's still fresh in your mind. If this video saved your math grade, hit that thumbs up button and subscribe so you don't miss Chapter 4, where we finally start getting into ratios, rates, and proportions. Keep practicing, and I'll see you next time.